Ladies and gentlemen, we are here. We are finally here. It has been a year-long endeavor. We've laughed, we've cried, we've learned a lot more about each other than we ever wanted to know, and now we're here at the final exam, Spring 2017. A few details. First and foremost, this exam does only cover what we talked about in the second semester. Especially if you're taking it dual enrollment, these were technically two separate classes. 201 and 202. This exam is only for 202. Now, there is a 3-hour time limit. Generally, most people do not take that long, which means bring something to entertain yourself, because you are required to stay in your seat for the duration of those 3 hours. With possible other exams going on elsewhere, we can't just have you roaming the building. So, bring a book, bring a device, bring something, so that you can enjoy whatever you need to enjoy quietly. It'll consist of 30 multiple choice questions, each of them worth 1 point apiece. There will be some sort of a lab-based question. That'll be worth 10 points. And I had originally made this document before I made the exam. There will in fact be 2 diagrams that you need to work on, 10 points each. And finally, there will be 10 free response questions, and just like the fall semester exam, you will decide which 8 I will grade. You are welcome to attempt all 10 if you want to, but when you hand in your exam sheet, you need to have 2 no's circled, telling me not to grade those, and 8 yeses. If you do not, I will randomly pick the ones to grade. Honestly, I'll probably pick the ones with the least amount of writing and the least amount of effort on my part when it comes to grading. That might not be the best for you. You all know what you know and what you don't know. Again, you are allowed a sheet of paper of handwritten notes. It can be 8.5 by 11, or it can be one of those longer sheets that I've given you in class in the past. If you need one of these longer sheets and haven't gotten it yet, come see me. You are allowed a graphing calculator. Again, please, 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 please let me know ahead of time if you need me to provide one for you. Now that we've got all 90 of you taking the exam at once, calculators won't be as plentiful as a standard class test where there's just 20-some of you. So, while I do have many calculators, I don't necessarily have 90 of them. So please, 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 do let me know ahead of time. Now, the document that I'm going through right now really just serves as a menu of concepts. It is not intended to be an exhaustive list of what you need to know for the exam. Basically, what I mean by that is don't just jot down what you see here and expect that you have fully studied for the exam. That's probably not the case. The best way I would go about it would be this. I would start with this document, make sure that you've got everything from here on your cheat sheet, because I'm not going to ask any question that I don't list here. However, I would then go back and maybe put some example problems, especially for those topics that are a bit fuzzy or confusing for you. Never ever hesitate to get in touch with me for questions if you want to work some additional problems. I'm here to help you in the days leading up to the exam. First and foremost, you gotta know units. This has been a year-long struggle, but you must know metric prefixes. Specifically, you're going to need to know nano, micro, milli, centi, and kilo, at the very least. There's a lot more of them, but these are the ones that you're absolutely going to need to know. Not only do you need to know what they are, you're going to need to be able to convert back and forth between one of them with ease. One way to do that is the unit conversion staircase. This helps some people, it does not help others. But remember, if you move to the right on the staircase, it's like moving the decimal place to the right, that number of spaces. If you move to the left, same deal as well. Feel free to extend the staircase even farther to include micro and nano later on if you need to. Vector addition. Everything that we've done, well, not everything, but a lot of what we've done in class has involved vectors. So make sure that you at least know how to break down a vector into its xy components, Make sure you know how to add any two vectors. Add up the x's, add up the y's, make sure one direction's positive, one is negative, and so on and so forth. So if I've got one vector pointing directly to the right and one vector pointing directly to the left, that's super easy. They're already just in x components. Then we started the year back in January. It was frigid, and it steadfastly refused to snow. And we started talking about electrostatics. We began with the elementary charge. Now, protons and electrons have the exact same charge, but protons are positive, electrons are negative. This charge is 1.6 times 10 to the negative 19 coulombs. Sometimes you see it denoted as just little e. I will give you that constant on the test. In fact, just about any constant you need to know, I'll give you on the test. Now, protons and electrons therefore have the same charge, but they got different masses. Neutrons, meanwhile, are neutral. They have no charge. A few things to also know about charges. Charge is quantized. Here's what I mean by that. I can never have an object with 1.5 times the elementary charge, because I'm not going to get half an electron piled on something. It's only electrons added or electrons taken away that causes charge. Not only that, they're conserved. So if two objects come in contact with each other, the total charge of the two objects is going to remain unchanged, even if the charge of object 1 versus object 2 might change from before versus after. When you add up the total charge of the system, it's going to be exactly the same, always. Then we started talking about forces, because what's a physics class without forces? Starting with Coulomb's law. Coulomb's law is K Q1 Q2 over R squared, where K is 9 times 10 to the 9th Newton meters squared per Coulomb squared. It's called Coulomb's constant. Again, that will be provided for you on the test. But it might not hurt to have in your back pocket to use anyway. Now the Q values, Q1 and Q2, those are the two charges. So notice, even if one charge is way, way, way bigger than the other, to find the force on it, you multiply the two charges together. They both feel the exact same force. And R is the distance between them, and again, F is the force that both of them experience. Now, a couple of things about Coulomb's law. It is a vector. Force is a vector, meaning it's got a magnitude, it's got a direction. The equation for Coulomb's law is good for finding the magnitude, and that's about it. If you throw in a negative for a negative charge, it's not going to really tell you much if I get a negative force. Instead, what I would do is ignore any negatives except for those in the exponent. Like 3 times 10 to the negative 3 is not the same thing as 3 times 10 to the third. So in exponents, yes, because that just tells me which way to move the decimal point. But if it was negative 3 times 10 to the negative 3 coulombs, I would ignore that first negative. So use Coulomb's law to find the magnitude, and then figure out the direction for yourself. If it's a proton and a proton, they're repelling each other, so it would be pointing directly away from the other proton. If it's a proton and electron, they're attracting each other, they'll be pointing towards each other. We talked a bit about grounding too. Grounding is just the process of connecting generally a conductor to an infinite reserve of charged particles. That infinite reserve is pretty much neutral because there's infinite protons, infinite electrons. So charges can go back and forth between the object and this infinite reserve. Sometimes you can use it to discharge an object that's charged up. If there are too many electrons built up on it, they will run to freedom if they can. You can use it to also charge an object through a process called induction, which we'll talk about in just a second. Polarization is what happens to conductors when you bring a charged object near them. The positive charges don't move at all because they're stuck in the nucleus. It's the electrons that are moving. So if I bring a positive charge nearby, electrons will go running toward it, leaving behind a net positive charge on the far side. If I bring a negative rod near a conductor, the electrons will flee to the far side, leaving a net positive charge on the near side. With an insulator, they get polarized too, just not as dramatically. Because charges are not free to move around insulators, They only get molecularly polarized. And some differences between conductors and insulators, there's actually not a lot. Both of them can be neutral or charged. The way they get charged may be a bit different. Conductors via conduction and induction. Insulators, you just rub two surfaces together. The only difference really is whether or not charges can freely move around inside there. So, like I said a few seconds ago, we're going to talk about conduction versus induction. Conduction is charging by contact. Conduction, contact. Basically, electrons will flow to where there are fewer electrons. And both objects end up with the same charge eventually, if they're left in contact long enough. If there's just quick incidental contact, they might not have the same charge afterwards. But the total charge between them will still be the same. Induction is what I call charging by trickery. You start with polarization, then you give electrons either a path out or a path in, depending on what the charge of the object is, and the two objects in question end up with opposite charges. So here are a couple of diagrams. Conduction, touch them, electrons directly transfer from one object to the other. You end up with two objects of the exact same charge. Not necessarily the same magnitude charge, but the same type of charge, positive or negative. And it works to either get a positive or a negative charge. For induction, one way you can do it is bring a charged object near a neutral object, ground the neutral object, and trick electrons into either leaving or coming onto that object. Another way you can do it is get two neutral conductors, stick them together so that electrons are free to flow between the two objects, bring an object nearby to get it polarized, separate them, and you got two objects of opposite charge. Nice. Then we barreled forward into electric fields. An electric field is just, it's the amount of force per coulomb of charge that a positive charged object would feel if it was placed in that point in space. So because it's relative to a positive charge, it always points toward negative charges and it points away from positive charges. So if I've got an electric field pointing to the right and I put a proton there, it feels a force to the right. However, if I've got an electric field to the right and I slap a negative charge there, it'll feel a force to the left. The way to find the magnitude of the electric field, if it's caused by a point-sized charge, is K times Q over R squared, where Q is the charge creating the electric field, R is the distance away from the charge wherever you want to measure that field strength, and E is the electric field strength itself. Again, it's measured in newtons per coulomb. You could also think of it as the force that a charged particle is feeling in the field divided by the charge of that particle. That's another way to do it as well. A word quickly on forces and fields. Both forces and fields are vectors. Forces, fields, vectors. Again, vectors have a magnitude and direction. So like I said a few slides ago, ignore the negatives at first, except for in exponents, obviously, unless it changes the value of it, the magnitude of that charge. Find the absolute value of the magnitude, either the force or the field, and then figure out the direction for yourself. Now, voltage, on the other hand, is not a vector. It's a scalar. So voltage problems are actually a lot nicer. To find the voltage, if it's created by a point-sized charge, it's just K times Q over R. I'm honestly not sure why on this slide I made the Q capitalized. Q is just a charge, just like in previous problems. So Q is the charge of whatever's creating the voltage, K is Coulomb's constant, R is the distance away from the charge wherever you're measuring. Again, like I said, it's a scalar. So the nice thing, basically, for any of these problems, if you have multiple sources of force, multiple sources of a field, or multiple sources of voltage, find each contribution individually, and then add them together. It'll either be vector addition or just standard good old scalar addition that you're used to. In this case, it's good old scalar addition. So, with voltage, because it's not a vector, you can't ignore those negatives. So I can get a positive voltage or a negative voltage. Find each value individually at the point in question, and add them up. Done. So this is a little table just to remind you how to treat vectors, how to treat scalars. It's what I've said several times over, so I won't bore you by saying it again. And finally, we wrapped up the electrostatics unit by talking about capacitance. Capacitance involves two parallel plates, each having built up a charge, and that charge is the same magnitude but opposite sign from one plate to the other. Because of these differences in charges, positive to negative, you get a change in voltage between the two. So I can find the capacitance as Q equals C delta V, where Q is the magnitude of charge on one plate, C is the capacitance measured in farads, and V is the voltage measured in volts. Cool, cool. And this wrapped up electrostatics, so this will wrap up my first review video. Stay tuned when we'll talk about circuits for video 2. Peace.